And that never has happened before. Interesting. So today, what was going to do is kind of like start showing you some of the uses of like these matrices that we had defined. I'll do kind of like the most simple case. By the way, I'm almost done writing some new problems for you to work on. I tried. I mean, my intent is not to give you too many problems, but like the ones that I give you, hopefully they're kind of like interesting. Like, and so. Uh, Today we'll talk about the Laplacian matrix for a graph, which has also applications for like signal analysis. So I'll tell you how that's related to Fourier series and this other stuff. I'll put some extra problems about that also like for you to take a look at. But like Fourier series is like a nice topic, and it's kind of like nice to see like a discrete version of that, which is what you can do with this like Laplacian matrix. So I'll explain some of the ideas today. But we'll continue talking about that next time. But it is a useful concept. Okay, so just to kind of like yeah, like just to kind of like give you like an introduction of what we're going to discuss today. So we want to understand as we have been saying, we're working with the simplicial complexes, right? And the simplicial complexes, you know, essentially the way they're built up, they're built from like a collection of vertices, right? So you have like vertices, and some of those vertices you can join by edges, right? So maybe this is like you have these relations, right? And some of those edges could also kind of like be connected through triangles. Okay, so there could be a triangle here. What makes this a simplicial complex is that the moment that, for example, the triangle is present, then all the edges of the triangle have to be present in the complex. So that's what we were talking about last week with these monotone Boolean functions. If you remember this closure condition, that the moment someone is listed, then all the subsets must be listed as well. For pictures, like this is more or less the most I'll try to do. From time to time, I'll try to draw like a tetrahedron or like a pyramid, but kind of like the idea is that this can go on, right? So you could also imagine connecting the vertices with a pyramid, like a tetrahedron, and like higher dimensional generalizations of that. So, but what I was saying, like, is that in this case, um, for example, if you were to give like an arbitrary, if you are arbitrarily label the vertices, there's nothing intrinsic about the label that you're using. Like in this case, I had four, so V0, V1, V2, V3. So the complex kind of like at a combinatorial level or just like from the set theory perspective, the way to list as a list of entities, you write a set for each of the vertices, right? And then um, the edges, you can think of them as being defined in terms of the pairs, right? So in this case, there's an edge that goes from V0 to V1, right? So kind of like our convention will be to refer to these edges kind of like in an increasing order, meaning that, when I refer to this edge, like, if I were to draw like an arrow, if I were to draw like an arrow, it would always go from like the lower index to the higher index. So something like this. Okay. But as a list, I'll just write V0, comma V1, and then V1, comma V2, and then V2, comma V3, and then V1, comma V3, right? So there's four edges. And then to refer to the triangle, again, you refer to it in terms of these vertices. A triangle has three vertices, and you list them in increasing order, right? Which is V1, V2, V3. Okay. So that is one way to think about the simplicial complex. Um, and like in this case, what I was telling you is that just to kind of remind you what we were doing last time, because this would be useful. You can, so you see, what I just did was kind of like organize the data according to kind of like dimension, right? So the vertices are in a sense zero dimensional, the edges are one dimensional, and the triangle is two dimensional. So this is kind of like you know, so this is zero dimensional information, this is one dimensional information, and two dimensional information. And again, like when I use the word dimension, it could mean that literally I'm thinking about this as kind of like some actual picture in actual physical space. But you can also think about this kind of like in an abstract way, where maybe there is it's being produced out of like some data that you have collected, and there's some relation between the data, right? Like so, in the social sciences, like that's kind of like easier because it is kind of like this friendship, relation that we had discussed, right? Like so, for example, where you would draw an edge between two people if they're friends, and a triangle could represent that they are like all friends with one another or something of that sort. So like in that case, it's like this is more kind of like a pictorial help, right? It's because it's not that there's literally like a triangle, in the social relation context, right? But it is a useful thing to just kind of like use as an analogy. Um, and then you would, right, and so you would organize these different dimensions, right, like the vertices, the edges, and the triangles into vector spaces of different dimensions, right? So actually, let me use three different colors. So for the zero-dimensional thing, the vector space would be R4, right? Because there are four vertices. For the one-dimensional thing, the vector space would be also, I guess, R4, right? Because there are four edges. And then you know, for the two-dimensional thing, it would be just a copy of R, right? Because there's a single edge. Okay. So that's how you get the three vector spaces. And the idea is that kind of like the way you're thinking about each of these vector spaces is that, again, like for example, for the third one, which is R4, like the purple one, um, it is four-dimensional, so it has a basis, right? And you think of like the vertices themselves as a basis for R4. So kind of like in an abstract way, each of the vertices represents you know um, a basis. So like a basis here would be V0, V1, V2, V3, meaning that every vector in this space is kind of like a linear combination of the vertices. Again, kind of like as a formal, what mathematicians call like a formal sum. Um, right? So a vector here would be a linear combination of these vertices. There's going to be an interpretation again, which I can mention before, in terms of a function, which I'll go back to in a moment. And then the other ones are like kind of like the same. So like the basis for the other ones could be that the edges, you can label them in terms of these endpoints. So if you want, you can call them E01, E12, E23, and E13. And so a basis in this case would be like, a linear, a vector in this vector space is a linear combination of the edges, which in Kirchhoff's laws, like I think I'll go eventually back to the circuit analysis analogy, that could correspond, for example, to like an electric current, right? Like you have some current passing through the wires. So, like a current, like, it's kind of like imagine for each edge, there's like a electric current passing. And so you can take a combination of if you want to have like a single thing that represents like the information about all the electric current passing through the different wires, you can write it down as a formal sum, where it's like a linear combination of the edge times the current going through that particular edge or wire. And then for R4, the basis would be the triangle. Okay, so it would be this triangle, which I'll just call T for triangle. I mean, not going to be super, strict about the notation here. So 1, 2, 3. And again, like that's just like a way to refer to the to this two-dimensional thing. Is that okay? Is that making sense so far? So good. And again, like the map, the idea is like these maps that we were talking about before, they just kind of like, in a sense, gives you the boundary of each of these things. So for example, um, the idea is that there is something that takes an edge and sends it to its endpoints. That's called like a boundary map because it literally is giving you the boundary of the thing itself. So in the notation in algebraic topology, which is kind of like the area of mathematics that studies this type of topics, it has like a kind of like a slightly odd notation, maybe because it's kind of like this symbol that appears when you talk about partial derivatives from Calc 3. It's kind of like the same del symbol from the partial derivative. But I mean, it just happened to be used. I suppose that you cannot keep inventing new symbols for things. Like things at the end get repeated. Like pi is like if you ever take probability theory, like you'll see pi is like for the actual number and also for probability distribution. Sometimes like it has so many different uses, that it can be confusing at times, but okay. So the one just means that it goes from something one-dimensional to something zero-dimensional. And so, for example, there would be a map here, a linear transformation of a matrix, which you would call del2 or the second boundary map, because it goes from something two-dimensional to something one-dimensional. Um, so that's kind of like what the indices like represents. Like the number here tells you the dimensionality that you're starting at. So del one starts at dimension one, and del two starts at dimension two. Okay. And so, for example, here, we had talked about this before, but what is del one? To specify the matrix, you just have to specify it on the basis, right? Because once you know what a matrix does on a basis, you basically determine what it does everywhere else. So each of these maps is kind of like just like a linear combination. Sorry, this should be the vertices V2. So it just takes it kind of like to the endpoints of the edge, but kind of like it does distinguish between the where it starts and where it ends. That's what the minus is for, right? So essentially, the one where if you think of an edge going from one vertex to another, then the one with the plus is where like the edge in a sense terminate. So like the ones with the plus, if you like fluid dynamics, those are the ones that you would call like sinks, right? Because if you think about it, for example, P3, right? If you think about this kind of like as a fluid flow, and actually that would be useful because later we'll talk about the divergence and the curl and all these things in that context. But if you thought about this as a fluid, right, the water is kind of like flowing into here, right? So it's kind of like it kind of like sucks in the water, so it's like a sink, and it like the water is kind of like emanating from V1. So V1 is what you would call a source, like in electromagnetism also, so in the kind of, if you look at the electric field lines, it goes from positive charge to negative charge. So in this case, like the way you would draw the edge is going from like, I don't know, the proton to the electron or whatever. Um, and then for the other one, for del 2 or the second boundary map, it is a linear combination. Is what we were talking about. It's kind of like an alternating sum. So it's plus minus plus, where you just delete one vertex at a time. So when you delete V1, you get V2, V3. So it would be the edge 2, 3 minus, and then when you delete the second one in the middle, you get the edge for 1, 3. So minus the edge for 1, 3 plus the edge for 1, 2. Okay. So and again, like I want to focus more today in what happens with the first map, this boundary map one. So I won't write like the general formula today, but like it always goes like that. It's plus minus. You just delete one vertex at a time, and that more or less defines it in full generality. Okay. Is that making sense so far? And now what I want to define first is what when is a complex path connected? So that's a useful concept. Um, Even like in this sense like of cluster analysis, where you want to separate things with whether first on whether you can connect them by a path or not. So again, like kind of like the friendship is a good analogy of that, because if you thought about it like a social network, right? Like, Facebook, Instagram, whatever, or like each user is, each user is a node on the simplicial complex. I mean, assuming that you could represent that by a simplicial complex, probably not, because like, well, I guess like the closure depends on how you define it. Um, I think it would be fine if you think about like the relation being kind of like being followers of one another or something like that. Like you would draw like an edge, maybe if some a person X follows person Y, or something like that. And you could make it symmetric, maybe even like at least one follows, at least of the one follows the other. Um, and so, well, anyways, what I'm saying is that you could imagine like, oh, maybe Alice follows Bob and Bob follows Charles. So through Bob, right, Alice is connected to Charles. So there's kind of like a path, that takes you from Alice to Charles, even not necessarily in one step, but in two steps. But like you could have entirely separate groups of friends, right, of followers, like where no one follows the other group of people, right? So those are can never be connected through a path, of followers. Okay, so that is we want to define that, because the idea is that this first map kind of like gives you like a algebraic way in terms of linear algebra to count how many groups of people, or like data sets you have in this way. So the idea is that if you have a simplicial complex, and let's say you have two vertices, and you're given two vertices. Well, I mean, I don't, like the vertices, like they could be called, I'll call them V and V prime, like so that, so you have a vertex V and a vertex V prime, right? So you want to say that they are path connected, right? So what is it going to mean for these two vertices to be path connected? Literally that you can find a sequence or like a list of edges, a list of edges in the simplicial complex where like the first edge maybe starts at V, and kind of like if you concatenate them, you terminate at V prime. Okay. Um, so you say that they're path connected. If you can find a sequence of edges, you know, which are like, I'll call them like, just like E1, H1, H2, F, H3 up to Hn, where, you know, the H1, let's say, is V followed by another H, which I'll just call V1. So basically, again, like just to kind of like represent this pictorially, it's kind of like well, sort of like a recursive definition, right? Like like there's an edge that takes you from V to V prime. Okay, so this is represented by this edge that I'm calling E1. Okay, and the second edge goes from V1 to another edge, right? Which I'll call, sorry, to another vertex. So E2 goes from V1 to this other vertex V2. So, this is maybe, why am I calling this V prime? So I should have called this V1. Sorry about that. So this is V2. Okay. And you kind of like go on onto the nth step, right? You can see how I'm defining this, and the nth edge would be Vn minus one until V prime, right? So at some point, again, just to kind of like make it look path connected, I'll just pretend that there were three edges, right? But kind of like the idea is that this would be like, for example, En and En edge En. Meaning, like, and again, more verbally, that you can concatenate. So basically, you're saying that two vertices are related if they can be concatenated by a sequence of, by a sequence of edges, by a finite sequence of edges. So two vertices are path connected, or can be maybe I should not that they're path connect. Maybe I should have called them connected by a path. That's what I meant. I mean, path connected would be the name of. Well, I guess path connected is fine. Um, so you're saying that two vertices are path connected if they can be if there's a if you can concatenate if there's a finite sequence of edges can be concatenated, and which kind of like pictorially takes you from V to V prime. Is that making sense? Uh, and it kind of like in this case, like it doesn't matter. Like the orientation. So like, you're just thinking about it like kind of like as a list. So if the idea is like you kind of like make this trivially symmetric. So if there's a path from V to V prime, you can kind of like run it in reverse, and that will give you the path from V prime to V, right? So this relation is kind of like a symmetric relation. It is transitive, right? As you can imagine, right? Because if V is connected to V prime and V prime is connected to V double prime, right? So there's a sequence of edges that takes you from V to V prime. There's a sequence of edges that takes you from V prime to V double prime. So you just concatenate them at V prime, and then so it is symmetric transitive. And if you want, you can just say that every vertex is path connected to itself, like just stay still, right? Like don't do anything. So it's kind of like a special case, you can add the reflexivity kind of by default. So essentially, all that I'm saying is that just in terms of this, you can kind of like define an equivalence relation. Uh, and the equivalence classes are called the path components. So essentially you can turn being path connected into an equivalence relation whose equivalence classes are called the path components of the complex, of the simplicial complexes. So that's it, like, more generally, this would be called the connected components of the complex, more generally, like in more general context, these are called like connected components, generally. So again, like if you think about it, in the context of like the social networks, right? Like if you drew an edge for like a friendship relation, then then you would say that like the connected components are kind of like groups of friends in the sense that they are like through acquaintances, like at least that you're appointed a friend of, if you belong to the same group of friends, that you are a friend of a friend of a friend of a friend of like, of some friends. So, you know, in the context, in the social networks example, you would say that two users, two users are path connected if you can find a sequence of users where, so let me say it like this. Um, the vertices are the users of the social network, and an edge corresponds to users of the social network, and the edge and an edge corresponds to a relation where two users follow each other. Let's say, just to make it symmetric more clearly, where they're mutually following each other. Follow each other. Where two users follow each other. So again, like the network, kind of like just to do like something more pictorial, you could have like if you were kind of like for a classroom and students, like, you could have like a really popular person, maybe, he's like follows many people and they follow him back, like, because I'm thinking about it as a mutual relation. And then there's this like separate group of people, like a separate clique of students, which are doing, are doing their own thing, and they don't interact with one another, right? These two cliques of groups. But again, kind of like the idea of like the path connectedness is that with the red vertices, no matter which one you choose, which of the two of the red vertices you choose, you can kind of like connect them through like a sequence of edges, and same with the blue ones, but there's no way to go from one of the blue ones to one of the red ones. If eventually any of these two follow each other, then come up, you're bridging the gap, right? Like, and now there's only one path component. But as in this example, there would only be two path components, right? That making sense? So far, so good. And so my claim is that you can count the number of path components with the null space of a matrix. That's kind of like the idea. There's a matrix that you can define whose null space, the dimension of the null space gives you the number of path components. Okay? In the context of graph theory, that's called the graph Laplacian. But again, you can do this for any simplicial complex. So you could have triangles, you could have pyramids here in the network, but still, like, that doesn't like kind of like affects like the path component part of it. So kind of like the idea, my claim is that there is a matrix um, with the property that the dimension of its null space or kernel if you prefer that word. I don't know which one you have seen in linear algebra, null space or kernel, but both are synonyms. The dimension of the null space or the kernel gives you the number of path components of the complex, of the simplicial complex. But again, you can think about it as a network or graph in this case, you know. Okay, so the idea that the way this matrix is defined is that it is defined as in terms of this Laplacian matrix that I was telling you about. So this matrix using this Laplace matrix construction. Laplacian, oh my God. Okay, so just to kind of like go back to what we had, the idea is that when you have the complex, you have a vector space. One of the vector spaces, which is like the one-dimensional one, it has a dimension equal to the number of edges. So let me write it like this. Okay. And then you have this other vector space whose dimension is the number of vertices. And this is kind of like the zero-dimensional component of the complex that I was telling you about. Okay. So there's this map or this matrix linear transformation that I defined a bit earlier today. Okay. So that is one of the linear transformations. And if you go back, actually, let me see if I can find it. When did we do all of this? Maybe it would have been around lecture 5. Yeah, see, where are you? Or lecture 6. So it would be, I think it would be kind of like around lecture 6. Yeah. Right, so this is where like we were talking about this like before. So the idea is that when you have some, like, let's say, some vector spaces and you have some matrices going around between three vector spaces, the Laplacian matrix was just kind of like you start in the vector space in the middle, you start the vector space in the middle, and with these two matrices, you just kind of like think of all the ways that you could go back and forth. So if you start with the middle, you could do A first and then go back with A transpose, which corresponds to this piece. Or you could have done V transpose and then go back with B, and that corresponded to this piece. So essentially, I'm going to do the same. The only thing is that if you look at what I have here, if you look at what I have here, I only have two vector spaces, not three. So you trivially add the zero vector space as a third one, because this is, this is one dimensional, this is zero dimensional. The next one would be negative one dimensional. And then there's nothing of dimension negative one, of negative dimension. So like you would just put the zero vector space here. So like you can think of it as being negative 1D, but the thing is that there's nothing of dimension zero, of dimension negative one, you know. So you could just put that there like the zero vector space. Because remember that the zero vector space has dimension zero, right? It doesn't have dimension one. It has one element, but it is a trivial vector space. So it's really just like an actual point. A one-dimensional vector space is like a line, right? It's not a point. So so in this case, like the map, right? Like there's only one matrix, the whose output is zero, is the zero matrix, right? So in this case, it's like you could call this the boundary zero. That's just like the zero matrix in this case. Okay. And so if you go back, again, if you want to kind of like reverse the arrows in this diagram, you use the transpose. So this would be the transpose of the going the other direction. This would be the transpose of the zero matrix, which is also like, just zero, right? Like there's not going to be anything interesting, but I'm still writing it down so that you can like see how it works in general. And the other one, you would transpose this boundary map. Okay. So again, like the matrix that I will be interested in, like the Laplace, like this Laplacian matrix, I'll just call it L0 because it's going to be defined for this vector space in the middle. So L0, and this is what people call in graph theory the graph Laplacian. So this is called the graph Laplacian in graph theory. But you can define this for any simplicial complex, but it is the same definition for any simplicial complex. Okay, so these is just like, again, if you started with the vertex, you have to imagine that you started here with the vertex and you want to think of all the ways using these matrices that you can go back and forth. Well, if you use the green path, if you use a green matrix, you get the zero matrix applied to a vertex, which just gives you zero, right? And then when you go back, it would just give you zero. So this one actually, in this case, doesn't give you anything interesting, but for the other situations, it will be interesting. But this one, because it involves the zero matrix, there's nothing that you really gain out of it, but I'll still write it down just so that you see it. So that you see it written down. And again, that represents a zero matrix, which kind of looks funny, but And then the one that is actually interesting for L0 is like the one that uses the transpose of the boundary map. So you can go with the transpose, and that gets you back to the vector space of edges, and then you go back with the boundary to revert yourself to the vector space of vertices. So that would give you. So again, this is what L0 is, because the first factor doesn't really matter. So the L0 is just the boundary map times the transpose of the boundary map. And so what is the size of this matrix? Again, it is, you know, if you think about it, it is a matrix that starts at the space of vertices and ends in the space of vertices. So it is a square matrix. It has to be a square matrix. And the input and the output is this space of vertices. So the size of the matrix has to be equal to the number of vertices times the number of vertices. So if there are like n vertices, it would be n times n, but I'll just say that the size of the matrix is number of vertices times number of vertices. Okay. So this one has size equal to the number of vertices times the number of vertices. So for example, in the complex that I had today at the beginning of class, there were 4 vertices. So this would be a 4 by 4 matrix. Okay. That would be the idea. And in general is that there is a Laplace matrix for each dimension. So like there's also a Laplace matrix that you can define for the edges. So that would be a matrix of size number of edges times number of edges. There would be another one that you can define for the triangular pieces. So that other one would be size number of triangles that times number of triangles. So you will have kind of like a sequence, like a list of these square matrices, one for each dimension. But I'm just trying to say that even this one already captures interesting information because it tells you kind of like the number of path components of your complex. Okay, which again, like it may seem like I don't know, like how what are your intuitions are like. But if I tell you, oh, you have like a network of like 10 million users, right? Like figure out how many connections are, group them into well, it sounds circular, right? But group them into groups, right? Like try to put them into clusters. Like what I'm saying is that, oh, you can just solve that using linear algebra. You can construct this square matrix, find the null space of that, and the dimension of that null space would be the number of labels or groups that you get. And that is kind of, it's not a kind of obvious thing. I would imagine, like at the top of your head, like if you told someone, oh, you can just like use Gauss Jordan, right, to row reduce a matrix, and that tells you how many clusters you have. That is not like obvious. Like, and the cool thing is that also not only works for the number of clusters, it also works like the number of one-dimensional holes. That would be the null space, the dimension of the null space of this matrix of edges. And then the number of like triangular holes would be like the dimension of the null space of this like matrix of Laplacian matrix for the triangle. So kind of like all the holes of every dimensionality for each dimension, you can kind of count the number of those dimensional holes, and then that is a null space. That's kind of like the cool thing here. But this is but already this one is interesting enough. So that's why I'm focusing here because it does connect nicely with Fourier series and like other things that you again like maybe wouldn't expect at the top of your head. So I'll tell you also how that works. Okay, so now what I'm going to try to justify is my claim that this actually is related to the number of path components. So far, so good. Is making sense? Questions up to this point? Okay, so again, so what I'm saying is that my claim again is that my claim is that the dimension of the null space of this matrix is the number of path components. Okay. But what was it? Okay, now this is just linear algebra. What is a null space of a matrix? Are all the vectors that get mapped to zero, right? That solves a homogeneous system, right? So the null space of a matrix consists of all the vectors for which L0 V equals zero, right? Right, a vector is in a null space if it solves the homogeneous system. That was kind of like the condition for being in a null space. Second, so for a second. Now, in this particular case, now what happens? If L0 times V equals zero, right? This is going to be useful. What is L0 in this case? L0 is just like this matrix times its transpose, right? Again, the matrix just happens to have like a funny looking name, but you could have called this matrix A or B. It really is just like a matrix. It just like has like this funny looking notation. Okay? And now I'm going to do a trick which maybe I used before, but it's like a useful trick to see multiple times in your life because it's like it's very useful. I'll just take the dot product of both sides of the equation with the vector v. Like, this is a vector equation, right? So I'll just take the dot product with v. So I'll do v dot this thing equals v dot 0. Again, it is an equation, so you're allowed to do these sorts of things, right? Like a vector equation, you can take a dot product on both sides. Okay, so far so good. Everyone with me. Okay, now I have to use the magical property of the transpose, which again is like a very important thing to kind of like internalize. So the magical property of the transpose is that you can move a matrix. Like again, here the matrices all appear on this side, right? You're taking the dot product between two things, right? Like this vector with this vector, right? So if you notice, like the matrices are kind of like all on the second factor, right? So the magical property of the transpose is that you can move one of these matrices to the other factor, but the price for moving it is to transpose the matrix. So you can move the matrices between the factors, which is like a very useful thing. But it's kind of like there is a penalty or like a trade-off that you do, which is that once, so in this case, I decided I want to move this matrix to the other side, but the price for moving it to the other side is that you transpose it. And on the right hand side, the dot product with the of anything with the zero vector is just zero, right? Is that okay? So far, so good. Oh, cute. But what did just happen? We just find that you're taking if you notice, like the two factors are the same, right? So you're actually just taking the dot product of a vector with itself, and the dot product of a vector with itself is its length squared, right? Like the magnitude squared. So actually, this is the same as saying that the magnitude squared of the transpose of this map of this linear transformation, the first boundary map transpose times v has length 0, right? Well, right, because if the length square is 0, then the length itself has to be 0. So there's only one vector in the world that has length 0. There's only one vector, the 0 vector. So that means that v itself has to be the 0 vector. So you find, oops. In other words, what this is saying is that, in other words, what this is saying is that V actually belongs to the null space of the transpose of this matrix of the one transpose. So what I just proved is that, let me write it like this. So if V is in the null space of L0, then V is in the null space of this matrix, the one transpose. Is that okay? Is that making sense up to this point? Questions up to now. So the thing is that it is easier to understand the null space of the transpose of the one because that's just like a single matrix. L0 involves the product, L0 was the product of two matrices, you know. So this is a product of two matrices. So that's harder to understand than just like the null space of a single matrix. So essentially, what I want to know, I want to know is what is the null space of this matrix. And if I can show that the null space of this matrix is basically the number of path components, that is more or less all that I need to know, because this is kind of like, this is already contained in this other one because, this matrix is like a product of the one with the one transpose. So essentially, all that I need to do next is understand the transpose of this matrix, the one. Okay, so my goal now is to my goal is to understand. Okay. Yes.
So we said that if like V is in the null space of the Laplacian,
Mhm.
then it's in the null space of transpose. So that means like the implication like it's one way.
Oh no, it is a
So it's an if and not.
it's an if and only if. It's just like the other one. It's a little bit more straightforward, right? Because if, sorry, but it's good to write it down. So right, it is an if and only if. It goes both ways, right? Because if the vector is in the null space of the transpose, right? Then that means that the one transpose times V equals 0, right? Then you just multiply both sides of the equation. So, I mean, it's good to notice as well, but there is kind of like a more that direct proof. So, in fact, again, I can write it down in the more common linear algebra note. I'll write it down in the linear algebra notation. Um, so V belongs to the null space. Right. So I just proved, like, again, if I didn't have such a weird notation for the matrices, this is just like the same proof. This is the same proof as that the null space of a product A times B is contained in the null space of what that would be. Sorry, that the null space of A is contained, or the null space. Oh my God, I hate this notation. That the null space of B is contained in the null space of A times B. You know. Again, like in less weird, like the thing is, like these are just regular matrices, just with a odd name for them, relative to what you know in from linear algebra. But it kind of makes sense here because, right, if a vector solves b times x equals 0, then it does solve a times b times x equals 0, right? Because of like what we just did. So I want to understand what this matrix is. So the goal is to understand the transpose of this matrix. Okay. So again, yeah, and this is like a fun proof because like the bad idea for doing this is to kind of like think, oh, let me just write the matrix kind of like let me try to find the entries of the matrix and then I just transpose it. I mean, that is in a sense what the transpose is, right? But that doesn't tell you really what it's doing. So it's useful to, understand it's useful to actually understand what the transpose is doing. So kind of like an analogy, right? This is one of my, this is probably like my favorite matrix in linear algebra, like at least in 250. What is this matrix? Oh, well, this is called like a rotation matrix, and literally what it does is rotate the vector by theta degrees counterclockwise. So what this matrix does is that if you have a vector here and the rotation matrix, what it does is rotate this vector by theta degrees, by an angle of theta. So it goes counterclockwise. Okay? So if I asked you, oh, what is a transpose, right? If I ask you, what is a transpose of the rotation matrix, right? Well, yeah, of course you could transpose it and just tell me, well, it is this matrix, right? And in a sense, that is the answer. But if you just give me that as your answer, you're not telling me what the way to think about this matrix, right? So just transposing that matrix doesn't tell me anything about what the transpose is supposed to be doing in this situation. In this situation, it actually rotates the vector clockwise by theta. So it's kind of like a clockwise rotation. And that is actually useful. Just saying, oh, just change rows with columns it's okay algebraically, but it's not useful because you don't have a sense of what's the physical operation that's taking place, right? But if you say that this is kind of like kind of like a clockwise rotation of theta, then that is interesting to say, you see? So and that's kind of what I mean, like, so, I'm going to try to find the transpose of this matrix, but kind of like in this sense of like, I actually want to understand what it's trying to do, not just kind of like find like the matrix in terms of entries and transposing those entries, because that doesn't tell you really what's going on. So that's why it's more important to understand a matrix as representing a linear transformation, because you want to kind of like know what it's actually doing to the to the vectors and everything. Is that making sense? And it's actually like a very elegant proof. We should have enough time to do it today. So what is that? Okay. So again, just to put it as a diagram. Let me put it like this. So again, you had the vector space of edges, right? And this map, which I'm calling Del1, takes you to the vector space of vertices, right? So the transpose goes from the vector space of vertices to the vector space of edges, right? So it's important just to understand at the level of input output. So the input of this matrix the transpose matrix will be a vertex or linear combination of vertices, and it's supposed to produce edges somehow. Okay? Because these are linear transformations or matrices, you only have to understand what they're doing on a basis vector. Once you know what it does to a particular basis vector, by linearity, you know what it does on the entire vector space. So really, to understand what this matrix is doing, to understand this, you have to understand where V is like an arbitrary vertex of the simplicial complex, right? Here, V is any vertex of the complex. Okay. So far, so good. Questions? Yes.
Points that like all the vertices are like basis vectors.
Right. That's kind of like the thing to get used to, right? Like every vertex kind of like is a again, if you want it to be more concrete, right? You can kind of like map each vertex to one of the standard basis vectors of of R4, like for example. So maybe I can put it here on the top, right? Like so for example, here you could think of in this problem, you could have thought of V0. Let me copy paste it. Yeah, if you wanted to work with a more concrete representation, right? Um, you could have said, okay, this is, V0 is just kind of like 1, 0, 0, 0, right? And V1 would be 0, 1, 0, 0, right? And V2 would be 0, 0, 1, 0, right? And V3 would be 0, 0, 0, 1, right? Uh, I almost you can totally think of them in that way, but that's kind of like not the right way to think about them because it's too it's too context dependent because it depends on how you label the vertices for starters, right? So the idea is like the proof is more elegant if you never have to work with coordinates. It's kind of like you can do kind of like a coordinate free proof, right? It's kind of like similar to like vector addition, because again, what is the correct way of like adding vectors? The correct way of adding vectors is like the parallelogram law, where you just draw things. That is a correct way of vector addition. The incorrect way is to say, well, if you give entries U1, V1, you just add them entry-wise, which is true, and it's convenient for a computer to work like that, but that it kind of like doesn't capture the flavor of what's going on, right? So versus like just saying that, U1, U2 plus V1, V2, right, is U1 plus V1, U2 plus V2, right? Like this operation basically is like the algebraic counterpart to this picture, right? But it is better to have the picture because that way you understand what actually is happening. If you just say just add the entries, that you don't know what that looks like. So it's kind of like something similar like in here, right? When I say that you can think of a vertex as a basis, what I'm saying is that yeah, if you wanted to introduce coordinates, you could literally think of them as the standard basis vectors, like from Rn, whichever n is the one that you're working with. But the proof won't need that fact. It will be completely like form like without what people call like a coordinate free proof, you see. Is that making sense? Okay, so let's find out the formula. Okay. It's like a very elegant thing. So again, this thing is supposed to be, um, you know, this thing is supposed to live in the vector space of edges, right? What does it mean to be in the vector space of edges? It literally means that you're a linear combination of the basis of edges. So this thing, it is not necessarily a single edge. That's what you have to be careful with, right? Because the only thing you know is that this is supposed to produce something in the vector space of edges. So, the only thing I can know for a fact is that it is a linear combination of edges, okay? Which imagine like you have labeled the edges somehow, so you can write it as a sum that goes from 1 to the number of edges, of some coefficients times a particular edge. So the E's here represent like an edge. So somehow you listed the edges, you said, okay, I had 5 edges, so I'll call it one edge 5, edge 4, edge 3, edge 2, edge 1. Okay. So here each EL represents one of the edges. Okay. So here EL is an edge. Okay. And CL is kind of like when it's a linear combination, you are like there is some scalar, right? Like it's like the coefficient. So CL is just like a scalar. Is that okay? So far, so good. Okay, and now what I'm going to do again, this thing is a combination of edges, right? So I can take both dot product on both sides of the equation with one of these edges. Actually, maybe it's similar. I don't know if you remember like this from like linear algebra when you have like when you have, maybe I should write it here. How do you find if you have like an orthonormal basis, right? Maybe that's a good place to start, right? If you have like an orthonormal basis, in linear algebra, how do you find the coefficients in the linear combination? What you would do is that you take dot product on both sides of the equation with one of these like basis vectors. So you would do Vj dot V, right? Would be the sum over I of Ci Vj dot Vi, right? But if the basis is orthonormal, what does it mean for the basis to be orthonormal? It means that all the dot products are zero, right? Because they're mutually perpendicular. The vectors are mutually perpendicular, except when it's a vector with itself, right? So this sum collapses to just being like Vi dot Vi, or sorry, Vj dot Vj. But Vj dot Vj is one because it's the length square of the vector, and then on an orthonormal basis, you just get Cj. So one way to, when you have an orthonormal basis, one way to find the coefficients of the linear combination is just by taking dot products, right? That's in fact how it's done in Fourier series. Once you know that sines and cosines of different frequencies span the space of functions, then you just take dot product on both sides of the equation, and that's how you get like the coefficients of the Fourier expansion, which actually I'll put one of the problems for you to work it out, because it's kind of like the same idea. Does that make sense? See you soon. Good luck. Enjoy your event. So I'm going to do the same here. It's just again, here the dot product is with an edge because the edges are a basis, and you can think of them as an orthonormal basis. So like all the edges in this sense are kind of like orthogonal to one another, and so you take a dot product with any of these edges, which I'll call EM. Well, I should have, so. So you take a dot product with one of these edges, and so that's the same as taking the dot product individually. But again, this is supposed to be like an orthonormal family of basis vectors. So all this sum collapses, okay? And that just gives you Cm, so the mth coefficient. So this just gives you the mth coefficient. Okay, I'll just give you like the formula today for the transpose, and then next time I'll finish my claim. But we're almost there. So that just gives you Cm. Okay, but then what is this dot product? Okay, what is this dot product? So you can use, and this is like the fun part. Let me actually write it this way. Okay, you again, if you notice, like the transpose, like this matrix is affecting the second factor, right? But because of the magical property of the transpose, or you can move this matrix to the other factor. So you can actually write this as a dot product of the boundary map del1 of the edge EM dot the vertex V. Okay, is that making sense? Because again, like you can move, that's the beauty of the transpose, that it allows you to move the matrix in a dot product to the other factor as long as you transpose it. The thing is, like the transpose of a transpose is just the original matrix that you had. Okay. But now, what is the, you know, what is the the boundary map on an edge? Is again now I will draw like a picture. Again, you have to think that every edge is connecting to vertices. I don't know what these vertices are, so I'll just call them Vm and Vm prime, let's just say. I don't know what those vertices are, the names, like which particular vertices I'm working with. So, I'll call them VM prime and VM double prime. Okay, so, and I'm thinking like of the edge as again, like when you do the order, the boundary map, you do go from like increasing at index. So assuming that the one with the two primes is the one that has the largest index, so the boundary map on this edge would just be the endpoints of that edge, but sum. So this would be give you. But a dot product is distributive, right? So you can just take the you can take just like the individual dot products. Okay. And again, all the vertices are orthogonal to one another. So you have a vertex V, a vertex Bm prime, and a vertex Bm double prime, right? So all the vertices are orthogonal to one another. So if the three vertices are all distinct of one another, right? If all the vertices are distinct of one another, they just give you zero, right? Because if you have only three different vertices, like all these possible dot products are just zero, right? So this coefficient would be zero. I'm almost done. I'll just finish writing this out, and then next time we'll use this for something interesting. So this is zero if all the three vertices are distinct. So if V, VM, and VM double prime are distinct. So far, so good. Does that make sense? And then, okay, then the thing is like, if they're not all distinct, then B has to coincide with one of these two. It cannot coincide with both because we don't have loops actually in our complex. You don't have like a kind of like a loop, an edge that goes from a vertex to itself. We are only working with vertices that connect. Well, if it were like the same, then it's but it would be also if it would also give you zero, right? Like if it coincided. I mean, if you allow for loops, then like that means that the endpoints are the same. So like it just gives zero anyway. But all I'm saying is that if the three are not distinct, that means that the vertex B has to be equal to one of these two. So what happens if B equals Bn double prime? Okay, so let's think about that. What happens for a moment? Um, well, so this would be the dot product of B and double prime with itself, right? But like again, the dot product of a vector with itself is just a length squared, and because this is like an orthonormal basis, it's just one. So it just gives you one. It just gives you one if V equals Vm double prime, right? What does it mean? But more like qualitatively as a phrase, what does it mean to say that V equals Vm double prime? It means that V is kind of like the sink or like you know, the head of the edge, right? Like so B is where the edge terminates. So this is like where edge terminates. So when V equals Vm double prime, what that means is that the edge ends at V. Okay. So V is like let's call it like a sink. V is a sink. And the other possibility would be when V equals Vn prime. So now these two agree, right? These two agree, and this dot product would just give you -1. So, and here V would be a source, right? So that means that and again, this is like a very nice thing. I'm almost done. I'll just at least I do want to write down the formula. What I'm saying is that these coefficients, when you express, when you apply the transpose to a particular vertex, when you apply the transpose to a particular vertex, it gives you a combination of edges, but each of the coefficients in this linear combination is either 0, 1, or plus or -1. And it's 1 precisely for all those edges that terminate at B, and -1 for all those edges that start at B. Okay, so the formula for that's the last thing I'll write for today. The formula for the transpose of a vertex is super elegant because it's just the sum over all the edges that end at V minus the sum over all the edges that start at V. Okay. So just to kind of like maybe draw like the last diagram, and hopefully like you can imagine like maybe how this can be useful for like electrical circuits or like fluid analysis, like for analyzing fluids and other things. Because imagine like if you had like a simplicial complex, right? Like just to kind of like end this for today. If you had a simplicial complex and you have like 3 incoming edges, E1, E2, and E3, that terminate at V, and then you have 2 edges, which I'll call E4 and E5, that start at V. Then what I'm saying is that the transpose of V would be E1 plus E2 plus E3 minus E4 minus E5. You see? So it has like a very, and if an edge neither starts nor terminates at that vertex, it doesn't count in this transpose map. Okay? So it has like a very nice geometric interpretation because you're basically what the transpose does is count kind of like the edges that end at that vertex minus the edges that start at that vertex. So it's like a very nice formula. And you'll see next time how, once you understand that, it's easy to convince yourself that the null space of this map should be related to the number of path components. But I mean, it won't take too long, but it's a good place to end for today because anyways, it's already 5:12, so I can find a little bit over time. So I'll tell you about that next Tuesday. And by then I would have added some extra problems for you to take a look at, but they will be fun because they will involve this thing, Fourier series and other things like graph, like some signal analysis, like graphs and things like that that you can do once around the